previously, when we've discussed, molar properties or molar quantities, we were only talking about one chemical or a pure chemical. But now that we're dealing with mixtures, we need to be a bit more precise in our language to determine whether we're talking about the molar properties of the entire mixture or if we're talking about the molar properties of an individual chemical. Okay? So moving forward, we're going to use the following definitions. And so let the letter M just represent some extensive property of an entire mixture. Whether that property be volume, enthalpy, internal energy, Gibbs energy, M can represent all of those things. And since we're talking about the extensive property, that means that if you increase the system size, so let's say you add more moles to your system, your volume would increase, your enthalpy would increase, so on and so forth. Okay, so M is the extensive property of the entire mixture. Now molar M, so we're going to put the little squiggly tilde on there, that's just going to be that extensive property divided by the total number of moles in the mixture. So total moles of mixture. So that includes all the different components or all the different species in that mixture. So molar property of mixture. All right. So once again, the M could be volume, so you would have molar volume, or it could be enthalpy, entropy, internal energy, Gibbs energy. Moving forward, just to kind of give you a handle on, or give you something concrete to imagine, let's just focus on molar volume. Oh, whoops. Molar volume of a mixture with C components. And specifically, we want to look at how the molar volume depends on temperature and pressure. Okay. And so our molar volume, harkening back to chapter 6, when we think of the molar volume, it's not only going to be a function of temperature and pressure, but now since we're dealing with mixtures, it's going to be a function of its composition as well. It's going to be a function of the mole fractions of the different components that make up this mixture. And so V here is going to be a function of, species 1, species 2, and so on and so forth until we get to species C minus 1. Okay? And I should say that since we're dealing with mole fractions, the sum of all the mole fractions should equal to 1. Okay? And the reason that we're only dealing with C minus 1 mole fractions which I'll commonly represent using these brackets here. The reason we're dealing with C minus 1 mole fractions is because if you define what your C minus 1 mole fractions are, then the last mole fraction left over, xc, is just going to be 1 minus the sum of all these other things, right? And so basically, once you have defined all these mole fractions, that's all the degrees of freedom that you have for your system. Okay? So that's just kind of a general way to talk about mole fractions. But once again, to give you a better handle on this, let's just start with the simplest mixture, which is just a binary mixture, where the number of components is equal to 2. Okay? And what you could think of is, let's say we have a mixture of water and methanol, which is abbreviated as MEOH, and whose chemical structure is COH, H, H, H. Okay? and water's is, of course, this. All right, and so for the molar volume of our mixture, of our total mixture, it's going to be a function of temperature, pressure, and then we'll say the mole fraction of water. Okay, because once you define this mole fraction, you automatically know the mole fraction of methanol. Okay. All right, and so now that we've set up this system, we're going to do basically the same thought experiment we did in the previous video, where we're going to be taking a beaker full of pure methanol and we're going to be adding drops of water to it. So let's consider case of H2O, case of adding drops of water to a graduated cylinder filled with methanol. Okay. And each drop of water contains delta H2O moles of water. So essentially, for every drop of water we add, we're changing the number of moles in the system by delta N H2O. Okay. So we could draw out our system. So here's our graduated cylinder. We initially start with methanol in the graduated cylinder, and then we're adding drops of H2O. Okay. All right, and what we're going to do, since we have this graduated cylinder, it has the markings on the side that tells us the volume. What we're going to want to do is we're going to want to track the molar volume of our total mixture. Okay, where the x-axis here is going to be the mole fraction of H2O, and we're going to keep temperature and pressure constant so that we don't have to worry about those. Okay. All right, and so for methanol and water, we know what their pure molar volumes are. So for methanol, its molar volume is about 40.7 centimeter cubed per mole. Well, for water, its molar volume, so its inverse density, is 18.07 centimeter cubed per mole. Right, so water has a lower molar volume than methanol, and vis-a-vis a higher density. Okay, all right, and so we know that these are essentially the bounds of molar volume that the solution could take on. As far as once we start adding drops of H2O into it, what's going to be that molar volume? And so if we make the assumption that the solution is going to behave as an ideal solution, then we would expect that the total molar volume of the mixture would just be some sort of weighted average between these two extremes, right? And so graphically we would expect something that looks like this, so like a straight line. And so this is what we would get if we had an ideal solution. But when people actually go out and do this measurement, what they find is this instead. So when they do this actual experiment that we described, what they see is that the molar volume that they measure is actually lower than what one would expect for the ideal solution. Okay? Right? And so adding water to methanol, once again, if you take a look at the chemical structures, you can see that they're different. Right? And so this sort of mixture doesn't obey, the assumptions of the ideal solution. And as a result, we see that there's strong deviations from that ideal solution prediction. Okay?